Finally, it's time for quantitative analysis. Okay, so this is under the assumption that either you've done standard analysis and you have your standards ready for your quantitative analysis, or we've done the standard analysis for you. Should let us know ahead of time so that we can do that. But basically, before we get started, I just wanted to make the comment that WDS is wavelength dispersive spectrometry, and it works on the principle of X-ray diffraction, and X-rays that are being emitted off your sample by the impinging beam enter the spectrometer by hitting the analyzing crystal. And during the standardization video tutorials, I talked about the analyzing crystals. The crystals aren't actually analyzing the X-rays going through them; they're just diffracting them, or a small wavelength of crystals, depending on its position, at a particular angle into the Faraday cup detector. So I want to avoid confusion. Don't have a lot of time to do these videos, so kind of just want to show users how to use the instrument, not so much background. Okay. So if you're let's pretend right now on the stage we're located at a unknown sample. In my previous standardization video, we standardized olivine, so naturally on this unknown sample, which is a basalt from southern Chile, specifically a Volcán Planchón, which is just on the crest of the Andes, just southeast of the capital city, Santiago. This sample has olivine, and that's what we're going to analyze. So let's open up the Faraday cup on the EOS monitor. The scan generator's on, so we should see this is our video here. This is an SEI mode. Now, for thin sections in SEI mode, it's hard to differentiate between different phases, phenocrysts or microphenocrysts on this volcanic sample. So most people like to navigate in backscatter mode, which you would do by hitting signal and then hitting the comp button here. Okay. And now if you look over to your video screen, now we're seeing backscattered imaging, and now we can clearly resolve different phases in this sample based on density. The lighter phases are heavier, and the darker phases are lighter, meaning lower Z atomic number. So some of these really bright phases here are most likely iron or titanium oxides. The darker stuff is probably either plagioclase, and then the in-between is either olivine or pyroxenes. So I think maybe these would maybe be olivines, these would be pyroxenes. Okay, so let's navigate around and find a sample to analyze. Okay. Let's move around so you can find something. Okay, wow, this is pretty big. I'm guessing this is an olivine phenocryst. Okay, so if this is true, then we'll analyze this guy. We'll double check using the EDS. Okay, so first of all, let's make sure we're in optical focus, just so we know we're hitting the right sample. Yep, we are. Good. Let's turn our scan generator off, close our Faraday cup, open up the EDS menu, click on EDS, and let's hit acquire. And under operation periodic table, we should expect to find iron, magnesium, and silica. Okay, iron, the energy lines are displayed, so that's iron right there. Let's see, magnesium, yep, and silica. Okay, so basically we used EDS just to confirm that that was an olivine phenocryst. Okay, so let's open the Faraday cup and take a look at this giant phenocryst again. Okay, good. So this is our sample. Now we're ready to quantitatively analyze this olivine. So the first thing you would do is go to the offline menu and hit Analysis, and go to Quantitative Analysis. Now, if you're a new user, or a returning user, you want to hit on Sample. If you're right now, it's currently the group name is Ishita. Ishita's a user of our probe, so she has done all kinds of analyses in her group. If you click on the group button, these are all the different users for our probe. This is where they all store their data and do their analyses, their quantitative analysis. So if you're a new user, what you would do is hit New, and then right here you got to type in, I would generally type in your name, maybe. In this case, we'll just do video tutorial. Okay, so we're creating a new group, and then hit OK. So this is kind of like a big folder where you keep all your quantitative analysis, and then at the bottom here, if you want to start a new quantitative analysis, hit New, and here we can just say olivine example. Okay, so click OK, and then hit OK. Alright, so now in the quantitative analysis menu, you should select measure or measurement. Now go to correction method. What you want to do in this case, since we're analyzing olivine, we'd click on oxide, or make sure that's depressed or pressed. The correction method, we're going to use the ZAF correction method. You can, well, this one is our preferred correction method, and the microprobe, the data correction and the calibration system called ZAF is basically based on there are correction factors for Z, which is atomic number effects, that affects the collection of X-rays, and A stands for the absorbance, so different materials have different absorbance of these X-rays, which might lead to discrepancies in your data. And then also finally F is for fluorescence, so some materials emit secondary X-rays related to primary X-rays as they pass through them. So these are kind of like correction factors that that change as you collect your data. You multiply them by these correction factors and it gives you better results. Okay, so just make sure those two are selected and go back to measurement. Okay, let's go to element condition. So this is very similar to standardization, except you know, we're not going to analyze or repeat as many elements as we did when we were doing standard analysis. So if you click on elements, let's come up with our element list. Let's clear all of these. Well, let's clear the ones we don't need. There's no calcium, so let's clear that, or sodium, or aluminum, or potassium. So in this case, iron, magnesium, silicon, and let's add manganese and nickel right there. Okay, that should be the principal elements you're interested in if you're analyzing olivine. Okay.